Hi, let's get together for lab number 10, electrical conductivity. Conductivity means what? Well, some movement of electrons. I guess that's what happens in metals. But in solution, what moves? Ions move. They move in opposite directions, plus going this way, minus going that way. So conductivity has got to do with movement, or the ease with which charge, that is movement of charged particles, can be moved from A to B. All right, let's see if I can get into the screen mode here. Slide mode. Come on. All right, and then let's see if it will allow me to pick up a pen. Pointer options. I like to write. All right, so that's electrical conductivity. Moving on, and so we're going to ask the fundamental questions. Well, what controls conductivity? I guess, first of all, how do we measure conductivity and what factors affect conductivity? And then, well, let's measure a few of the everyday solutions and see if we can explain the conductivity. Things like orange juice. People like orange juice. Ooh, milk. Anyway, moving right along. Anyway, so here's the explanation of electrical conductivity. We said movement of ions. Movement to where? And who's driving the movement? Well, if we apply an electric field, let's think of DC this time, plus here minus, then these are electrical plates or conductors. Let's make them made of inert platinum. And then this is solution here. Then we can imagine anions going to the plus and cations going to the minus. But how do we measure conductivity? What when I give a number? Conceptually, we know this. In order to get conductivity, we've got to apply, gotta have a power source, some voltage source. And then we've gotta measure some current. And then we kind of just intuitively know if something is not very conductive, then the number should be low. If something is very conductive, the number should be high. And so with that, you can think of come on, it's not writing. There we go. Is conductivity related to current over voltage? You apply certain voltage, a certain current flows. If the current is low, then that's low conductivity. But it turns out also that the distance between the plates that we have, they matter. So put them apart, conductivity decreases. And so how about if we divide by the plate? So that's how conductivity is measured. Current over voltage divided by the distance between the plates. We like names. Somebody decided that this me here was gonna be called Frazier. Here. Anyway, moving right along here. So somebody decided that current or voltage is a Siemens, abbreviated S. So conductivity then is Siemens per meter, but that happens to be such a very big unit. It's like counting irregular persons' income in billions. That might not be a good idea. Anyway, so we go micro Siemens per centimeter, meter to centimeter, going smaller, Siemens to micro, that's 10 to the 6, and so there we go. So on our data logger, we will see micro Siemens per centimeter. Big number, micro Siemens per centimeter, very conductive. Low number, low. Okay, so ions in solution, how do they get there? We can put them there. So consider sodium chloride. You think of sodium chloride as sodium and chloride ions kind of stuck together, but when you put them in solution, they go their separate ways, and we write that as an equation like this: Na plus aqueous plus Cl aqueous. The aqueous means they're independent, doing their own thing, moving about in solution. And so under that scenario, then you can imagine the plus is going one way and the minus is going the other way. That's a strong electrolyte, meaning that all the ions exist, and for if you have 100, you end up with 100. Well, some molecular compounds kind of don't, they ionize, but they don't ionize, they don't go full ionization. So I'm sure you're familiar with weak acids. Weak acids don't go all the way, partial. Let's say in this case acetic acid, gotta know acetic acid, 5% ionization. It means if you set up with 100 of these, you only end up with roughly 5 on the other side. Haha, you have formed ions from a molecular species, but it's not 100% conversion. And so you guys are familiar with the term weak electrolytes. And then nano-electrolytes don't do anything. So here are things to consider. Well, the ions in conduct. So it must mean that the more of them you have. But what does more mean? It makes more sense to talk about concentration, since we're dealing with this. So what's the effect of concentration? The higher the concentration, the higher the conductivity. What's the relationship? Can I find the relationship? Well, okay. Next one. Charge. +1, +2. If you're moving, who's carrying more current? Effect of temperature. Movement. Higher temperature. What's the mobility at higher temperature compared to lower temperature? Moving faster, slower, whatever. And then, I don't know, I don't see it here. How about effect of size? Maybe it's not here. And then we'll test the conductivity of a number of things and try and explain it. So there is our conductivity sensor. It's got a little opening here, and the sensors are in here. And so between measurements, you want to rinse through that hole there to sort of wash off whatever it is in there. And then also to make sure that the solution in here is equal to the solution out there, you want to dip it in kind of 1, 2, 3 in order to enforce that scenario. Come in. So here's your conductivity sensor that you guys are going to use. Here it is. And that's the conductivity sensor hooked up to the data logger. What you want to note is that the conductivity sensor has a number of ranges. 0 to 100 microsiemens per centimeter. That's the most sensitive range. 0 to 10,000 and 0 to 100,000. You always want to start here, and when it floods, it will show this nice round number of 1,000. Then you go to the next one. If that floods, and you go to the next one. The measurements you're making should be a good fit with all those. And we're going to make these measurements in a test tube. And so in this case, concentration wise, how about 0.05 molar HCl, 0.1 molar HCl? That's in effect of concentration. Similarly, 0.050 molar acetic acid compared to 0.1 molar acetic acid. Now when you're done with those measurements, you can talk about the effect of concentration. But looking at the cross between HCl and acetic acid, you can then be able to contrast a strong acid and a weak acid. And then for the effect of charge, it'll be sodium perchlorate +1 -1, and magnesium sulfate +2 -2. Looking at those two, which one actually shows a higher conductivity? If it does show, whichever one shows a higher conductivity, can you rationalize and explain the results? For the temperature one, we're going to use an ice bath that is 0 degrees centigrade and room temperature, and then you can look at those values. And again, the idea is to not only record the values, but also be able to explain them. Everyday solutions. Well, let's see, not so much everyday. Here are a few of them. 0.010 molar sugar. How about Coca-Cola? It's probably Pepsi. The lady in this stockroom loves Pepsi a little better. But anyway, looking at those values and then others of regular compounds that you're familiar with. 0.1 molar NH3 ammonia. 0.1 molar H3PO4 phosphoric acid. And again, make those measurements and be able to look at by comparing those measurements, be able to make sense of what they look like. Again, remember to rinse the sensor between measurements in order to ensure that we don't have any carryover. And then the dip up and down ensures that whatever you're measuring inside is the same as whatever you have outside. So that's your lab today. Wear goggles at all times. That's the rule. I come wearing goggles, and you should wear goggles too. Today, all our solutions, as you can tell, are pretty benign, and so those can go down the drain. Just make sure you wash them with, rinse the sink with plenty of tap water. Have a great day. Bye.